This is section 9.2, Parabolas as Conic sections. It's entitled that primarily because the intro within the text reading, or learning, if you will, explains where the idea of parabolas, ellipses, and hyperbolas came from, which is as sections, that is, planes intersecting what we call a double napped cone. And I have a video that was posted on this lecture list right before this lecture. If you haven't viewed that yet, please do. It's a very well-made, animated video. So that's the intro part. Now that's a purely geometric definition for the parabola. In modern geometry, most often we use what's called an analytic definition of the conic sections. Circles are included in there as well. Circles, ellipses, hyperbolas, and parabolas. A circle being a special type of ellipse. Analytic means using formulas. Okay? And of course, this is still geometry. It's just that we're using formulas which they did not really use in ancient Greece when they came up with this conic section idea. They were doing things entirely geometrical without using algebra. Algebra hadn't been invented yet. And without using coordinates in a Cartesian plane, which is named for Descartes, who's a French philosopher who did not exist yet. So the way we define parabola most of the time in modern mathematics is as a set of all the points in a real plane that are equidistant, the same distance, from some point called the focus and some line called the directrix. So I have a picture here. Well, don't get to it yet. So the focus cannot be on the directrix. That's just because it wouldn't give you something that would be a conic section or that would look like a parabola. It would just give you the point, the focus. So for this class, the directrix is going to be either vertical in our Cartesian plane, that is our real plane, or horizontal. You can have directrix going in any direction, but you have to use some trig in order to write out the formulas. And that's really not used very often anymore unless it turns out to be central to your studies. So here's a horizontal directrix and a point that's not on the directrix, which is the focus. Okay. So you see it's still tied in with geometry. It's just you'll see we're going to give a definition that has to do with formulas. So if you pick any point, arbitrary just means any point on a given parabola with this directrix and this focus, then the distance, the perpendicular distance from that point to the directrix, if we call that d, then it'll have the exact same distance d from that point to the focus. Now, of course, as your point xy travels around the parabola, d gets longer or shorter, but those two distances will stay they'll stay the same as each other, but of course not the same as this d for this particular point. So the d is a variable, but those two lengths have to be the same. So this is a vertex. The vertex is directly between the focus and the directrix. It's halfway between. It has to be halfway between because it is on the parabola, so it is one of the points x, y, and that means the distance from the vertex to the focus equals the distance from the vertex to the directrix. It's not the same as the one I labeled d. It's a little bit shorter, right? But those two lengths are still the same between the vertex and the focus and the vertex and the directrix. And all the points on the parabola have that property, and that defines the parabola, in fact. Okay. We often call these distances P. You don't have to, they're actually, yeah, you don't really have to worry about that. This stuff on this page you don't have to worry about too much. It's just that we have to give you the definition for a parabola before we start talking about a parabola. We could kind of cheat and say a parabola is the graph of a quadratic function, but people don't like to cheat quite that much. So you know how a circle is the set of all points in a plane that are equidistant from a point that we call the center. And I think everybody knows that definition of a circle. So this is analogous for a parabola. Okay. So notice that 2p happens to be the distance from the focus to the directrix. So the vertex, I'm just saying the vertex is halfway between the focus and the directrix. Okay. Which, if you thought about it, it just comes directly from the definition. P is a constant, but the d changes as the point moves around the parabola. Yeah, so that's just a basic intro. That's the analytic definition of a parabola.